So hello, welcome. We are now in the Thursday of week 9. I don't even remember what lecture number this is, but this is Math 140 SCI. Okay, so we are continuing now with chapter 21. And for the first time, we will not be looking at just one sample, but we will be looking at multiple samples at the same time. So chapter 21 is on comparing two means. Comparing two means. Okay, thank you. Okay. And 21.1 will be on the two sample problems. Okay, two sample problems. For example, there are many situations where you have two different populations, and as such, you're curious about whether one population differs than another population. We've spoken repeatedly about, as an example to use in class, the average height of every American. Well, what if I'm curious whether the average height of every male American is bigger or smaller, or perhaps not equal to the average height of every female American? So I have two different populations. I have two different parameters, and I want to compare those parameters to each other. So I'm not looking at just one population by itself, but rather I now have two different populations. And I want to make conclusions. Is the difference between these two positive? Is it negative? Is this one bigger? Is that one smaller? Are they equal? And so on. So this is the idea of two sample problems. And what we have is population 1. And then we have population 2. And each population is going to have its mu and its sigma. So mu1 and sigma 1. And population 2 is going to have its mu2 and its sigma 2. Now, as a general rule, the mu, the mean, is unknown. Those are the ones that we're curious about. What about sigma? Is sigma known or unknown? Well, if you recall from what we did last time, we had two different scenarios. We had the case where sigma was known, and then we had a different case where sigma was unknown. Anyone recall the differences in what we did for when sigma was known versus when sigma was unknown? Anyone recall? Anybody? So when m equals, we substitute, okay, so yeah, so when sigma is known, we use z. And when sigma was unknown, we substituted that with s and used t. Does this ring a bell a little bit from the rest of you? Hopefully. But either way, yeah, t star, exactly. Okay, we had z star, we had t star. But either way, if you want to know mu's, or you want to compare the two mu's, you need to take two samples. You need to take a sample from the population 1, we'll call that sample 1, and you must take a sample from the second population, we'll call that sample 2. And each one comes with its X bar, each one comes with its SX. So we'll call this one X1 bar and SX1, and we'll call this X2 bar and SX2. Of course, there is one other thing that we should know about each of the samples. What's something else that we might care about each of the samples that might play a role in the problem? The size, yes. So they don't have to have the same size. And therefore, we're going to have sample size 1 and 1, and we're going to have sample size 2 and 2. And what's the procedure? We will take an SRS from 2 independent populations, or better yet, from, well, we'll just say populations, but what I mean by that is that the samples themselves are independent. For example, if I want the average height of every American, every male versus every female, I'm not going to take, for example, I'm not going to look at husband-wife pairs and do the husband and wives in a relationship, because they're not independent. Okay, there's a relationship between them. I know that there are relationships out there where the female is taller than the male, but those are relatively rare. So if I just take husband-wife pairs, I'll probably get a relationship which may or may not be in agreement with the rest of the universe. But we will take an SRS from 2 independent populations. And we will then, both populations must be normal. Both populations must be normal. And the, or, and at worst, they have similar shapes with no outliers. They should be normal. How is that different from a random sample? An SRS is a random sample. Each sample should be random, but when I take 2 SRSs, I got to make sure that those 2 samples have no connection between them. So an SRS here, an SRS here, maybe my example wasn't the greatest, because if they were truly an SRS, I'd be very unlikely to catch a husband and a wife pair. But in general, when you take your 2 samples, you have to make sure, just conceptually, that they are independent. So I can't off the top of my head think of a situation when they wouldn't be, but you know, you'll be reading a study or something, you'll be like, hey, wait a second, those aren't independent, or something like that. It might just pop out. Okay, but I can't see one off the top of my head. Maybe if I look through the book, I come up with an example. But this is the condition that you need, an SRS from 2 independent populations. Okay, they can't be connected. And then the question is, what do we do? What do we do with this information? Well, let's not forget, there's 2 approaches that we can take. Option 1 is form a confidence interval. Option 2 is to perform a hypothesis test. These are the 2 things that we're going to be doing for the rest of the semester: confidence intervals, hypothesis tests. Let's remember what a confidence interval is, because the confidence interval So we do that one first. I want to follow the book's order. The book. What does the book do? The book kind of lumps them together in the same section. So let's do both for the same problem, just to show how we can do both. So let me find an example here, and we will do both. Okay. So looking at the questions at the end of the chapter, we can do women talk more than men? This is on page 486. Do women talk more than men? Equip male and female students with a small device that secretly records sounds for a random 30 seconds during each 12.5 minute period over 2 days. Count the words each subject speaks during each recording period, and from this estimate how many words per day each subject speaks. Here's what we get. We have the following data. We have study 1, study 2. For women, we had 56 women in the first study. We had 27 women in the second study. There were 56 men in the first study and 20 women in the second study. Number of words for women. Number of words for women versus men were 16,177, 16,496, and they also provide the standard deviations for those. And I know this because they said it. For men, 16,569, 9108, 12,867, 8343. These are the studies. There were 6 studies according to this problem, and here are 2 of them. So the question is, does either study support the idea that women talk more than men? Does either study support this idea? So let's start with a hypothesis test for study number 1. What would the null hypothesis and alternative hypothesis be strictly for study number 1? So we're focusing only on those for this question. For study number 1, what would the null hypothesis be, and what would the alternative hypothesis be?
Is it mu is equal to 56?
Well, 56 is the number of women in the study, right? Not the mu that we're looking for. What are we looking for? We're looking to see whether or not women talk more than men, correct?
Okay, so it's 16,177.
What's 16,177?
The words that women spoke.
Well, on the average, that's the number of words that women speak. But if we're looking at women more than men, how can my answer not include the men's number? So do we know the average number of words spoken by women every day? Okay, let's call that mu1. If we assume women are 1 and men are 2, we do not know mu1, the average number of words spoken by women every day. Do we know mu2, the average number of words spoken by men every day? The true value, do we know them?
No.
No. So what are we testing to see about mu1 and mu2? What are we checking for?
If it's over like a 50-50.
Well, I hear what you're saying, but these are not percentages. These are totals.
Is it, can it be a proportion or no?
No, not proportions, because these are average numbers.
If mu1 is greater than mu2?
Okay, so the alternative that what we're checking for is whether in fact it's true that mu1 is greater than mu2. Welcome, Mariah, welcome. Was he guilty or innocent?
Neither. They haven't even picked the jury yet for the last 2 days.
Crazy. You got to go back?
Yep.
Jeez. Do you tell them you have a stats class?
They haven't even talked to me. I'm like way back in the list of jurors, although now they're going to be interviewing me tomorrow.
Crazy.
But yeah, I just listen to them interview everyone else and sit quietly. And so I can't even work on my stats stuff. It's so annoying.
What a horrible experience.
Yes.
That's
So
it.
I have to drive back in traffic all the way from the courthouse. But I'm here.
You're
That's
here.
important.
Woo, you're here. Okay. So the alternative hypothesis is that mu1 is greater than mu2. We're checking to see whether or not women talk more than men. So what would the null hypothesis be?
Mu1 is equal to mu2?
Yeah. I mean, what, if we're checking to see if women talk more than men, the mu1 is bigger than mu2. The null hypothesis is that neither is bigger than the other, right? That we're just going in with the assumption that they're equal. Why should one be bigger than the other? Now, we normally rewrite this as mu1 minus mu2 is equal to 0 versus mu1 minus mu2 is greater than 0. So there are,
Sorry?
yeah.
So would the alternative hypothesis be that men talk more than women?
No, we're testing whether women talk more than men. That's the alternative.
No, what's the null?
The null is that they're equal.
Okay.
Yeah, the null is that they're equal. The null hypothesis always gets an equal sign. At this level, at least. The null hypothesis always gets an equal sign
In this scenario, right?
in all scenarios.
Oh, okay.
In this class, the null hypothesis always gets an equality. So if you're ever in doubt, what's the null hypothesis? Just look for an equal sign, you're halfway home. Okay, and the alternative is either greater than, less than, or not equal to. Okay? So we're testing to see whether or not mu1 is mu1 minus mu2 is greater than 0. So this is a question about two samples. So before we do it by hand, let's take out our calculator. And who wants to take a sample, to a guess as to in stat test, which one we're going to do?
Is it two sample Z test?
Sorry, two sample, what do you say?
Two sample Z test?
If it's a Z test, we have to know sigma. Do we know sigma?
All right, so it's a two sample Z test. Oh, I said Z again. T.
I'm like,
Took a while. I was like,
I know I'm tired, but I'm pretty sure she said the same thing twice. Yes, it's a two sample T test. And when you go to the two sample T test, how many things do we got to plug in? And do we know them all? So go in your calculator to the two sample t-test. What's the first thing we got to plug in? Because we don't know sigma. We use the z-test when we know sigma. We use the t-test when we don't. And here we don't. Cynthia, you got that?
Yeah, thank you.
Okay. So what's the first thing we plug in for the two sample t-test? I mean, if you're on, guys, your calculator's out, you should be able to read it off. What's the first thing we plug in for two sample t-test?
Would it be the X bar?
Okay, X1 bar.
X1 bar, would it be the 16,100?
Good. And what's the next thing we plug in? What's SX1?
The standard deviation,
Which is what?
7,520.
7,520. What's the next thing we plug in?
Sample size, which
How
is
much?
56.
6. Okay, next.
And then for men, it would be 16,000. I think that's 509.
569.
Oh, yeah, 569.
Okay, what's next?
And then the standard deviation of 9,108.
Good. What's next?
Sample size would be also 56.
Also 56. What's next?
And then the what is it called? The U thing again? Sorry, I forget the name.
Mu. It's a sound that a
Mu.
French. It's a sound that a French cow makes. Mu.
Oh, the mu, whatever. You do equal to the second mu.
Is it?
mu.
Well, there is no equals there.
Oh, no, you're only doing the alternative. You do the greater than.
Greater than mu2.
Yeah.
And then how about the last one? What's the last thing we plug in?
Calculate.
Well, there's something before calculate. You kind of glossed over it.
The pool thing.
Yeah, the pool thing.
Yes, we'll put yes on it.
No, you're gonna put no on it.
Oh, it was already on there. That's why I was like, what?
Well, but what does it mean, the pool thing? And for those who don't have
I don't
the
know.
calculator, the very last line says pooled. Would anyone like to take a guess as to what the pooled stands for? And if you're wrong, you're wrong. But take a guess.
Something like combined.
How? Combined why?
Is it two samples?
What, and why would I combine the samples?
I'm just gonna guess because it's a two sample t-test.
Well, then it should, if that's the case, that it's always going to be pooled, then why would it give me an option? Right?
Mhm.
So the answer is the following. We do not know sigma, which is why we're using a two sample t-tests. But what if I came to you and said, you know what? I don't know sigma, but I know they have the same sigma. If for whatever reason I knew that they had the same sigma, even though I didn't know what it was, I would pool them together. In this case, am I given any information about what their sigmas are?
No.
In that case, I do not pool them together. And I calculate. And what do I get as my p-value? What is my p? That's right, Celeste. What is my p-value in this case? .5978. Celeste, excellent. And as a result of a p-value as 0.5978, what do I conclude?
We don't reject.
We do not reject the null hypothesis. There's a 60% chance, that we got the results that we got if the null hypothesis were really true. If something has a 60% chance of occurring and it occurs, do you question your assumptions? If my assumptions say that something has a 60% chance to occur and yet it occurs, do I say, oh, that's not good? No, of course, 60% is huge. I'm not going to question anything. So I do not reject the null hypothesis, and as such, there is not enough evidence from sample 1 to claim that women talk more than men. Sample 2 might be a different story. Because when I look at the means of sample 2, I see a much bigger difference in the means of sample 1. So let's just go ahead very quickly and do a test, another 2 sample t-test for sample 2. It should take all of a minute to plug in these numbers and hit calculate. All right, what's the p-value for study 2?
For the standard deviation, is that 7,970?
I got 14. Sorry if my handwriting is. I think it was 14. Yeah, 14. So what do I get? What's my p-value for number 2? .07, which is still not small enough to reject the null hypothesis, but it's pretty close, depending on what my level of significance is. Make sense so far? In this class, you will always be allowed to do everything on a calculator or crunch it. But certainly on the tests, the final calculator, you should know how to do it. You do not have to do these by hands. Okay, the calculator does all the work for you. But notice, we only need a few pieces of information to be able to determine whether or not we reject or do not reject the null hypothesis. Okay, so this was the hypothesis testing approach. Next, what about confidence intervals? What about a confidence interval? What about a confidence interval? For mu1 minus mu2. So someone remind me, what was the general form, recall, the general form of a confidence interval? What was the general form of a confidence interval?
X bar.
Okay, I'm going to write it as our statistic.
Statistic plus or minus the margin of error.
And what was it? And what was the margin of error?
Like the formula?
Well,
Or like another.
the general form was a Z or T star. In our case, it's a T star times. What was the one for the last example? We did sigma over root n, correct? But the problem with sigma is we don't know it, so we had to go to s over root n, right? But that was great for one sample. Now we have two, and each one has their own n, and each one has their own s. Correct? So how do we put them all together? So the answer is the following. S1 squared over N1 plus S2 squared over N2 in a square root sign. And Roni, I hope everything's okay, but go ahead. So the statistic plus or minus T star. And what is the statistic, by the way? In the last case, it was X bar, correct? Because X bar was the greatest approximation for mu. But now we're looking at the difference of two mu's. We have mu1 minus mu2. So what do we think is going to be a good estimate for mu1 minus mu2?
mu1 minus mu2.
But I don't know mu1 and mu2. How could I use them in my formula if I don't know them?
Can you subtract the means that we got from the study?
Yes. X1 bar minus X2 bar is a much better estimate than mu1 minus mu2 because I actually know these. I don't know mu1 and mu2. I can't subtract things that I don't know. So the general form of a confidence interval for mu1 minus mu2 is X1 bar minus X2 bar plus or minus T star times the square root of S1 squared over N1 plus S2 squared over N2. Now, if you recall, when we did one sample, every time I used T and I went to the tables in the back of the book, I had to give you something for those tables, didn't I? What did I have to give you for those tables? I had to give you a number. What was that number called?
Degrees of freedom.
The numbers of degrees of freedom, which was what in those examples?
N minus 1.
N minus 1. Well, how do I provide the number of degrees of freedom here when I have two n's? I can't quite do n minus 1 when I have two n's. So what do I do in this case? Anyone like to take a guess?
Can you take the average of both?
That's actually a pretty good guess. And it's true and it's not true at the same time. It's a weighted average. It's a weighted average, which is not at all obvious. I'm going to write out the formula, even though we're never going to use it, just so you can see how annoying and complicated it is. But the degrees of freedom in this case is given by the following formula. S1 squared over N1 plus S2 squared over N2 all squared, not the square root, but rather squared, and 1 over N1 minus 1 times S1 squared over N1 squared plus 1 over N2 minus 1 times S2 squared over N2 squared. This is the formula for the number of degrees of freedom for this situation. Ew is right. Yeah, ew is right. Who wants to calculate this by hand? Not that it's exceptionally difficult if you have your S1s and your S2s and your Ns. It's just like, why would I want to? Which is why, once again, we see how amazing it is that the calculator can do all the work for us, because it's just really, really, really annoying to do it by hand. Okay. Now, there are approximations to T that we make if we don't want to do it this way. But if you want the rigorous value of the degrees of freedom, this is it. And when you do it on a calculator or you do it by hand, this is what you get. As usual, let's load up Crunch It. Or I'm going to load up Crunch It here so we can see how Crunch It does the same operation. So give me a second to load it up here. Okay. So ebook. All right, let me start sharing here. And we're going to go to chapter number 21, comparing two means. And let's go to exercises. And let's pick a fun one. Are there any links to Crunch It here in the exercises? Doesn't look like it. So let's go back to probably section 3. Okay. All right. All right, Nintendo and laparoscopic skills. Okay. So in laparoscopic surgery, a video camera and several thin instruments are inserted into the patient's abdominal cavity. The surgeon uses the image from the video camera positioned inside the patient's body to perform the procedure by manipulating the instruments that have been inserted. It has been found that the Nintendo Wii, with its motion-seeking interface, replicates the movements required in laparoscopic surgery more closely than other video games. If training with the Nintendo Wii can improve laparoscopic skills, it can complement the more expensive training on a laparoscopic simulator. So 42 medical residents were chosen, and all of them were tested on a set of basic laparoscopic skills. 21 were given Nintendo Wii for 1 hour a day, 5 days a week for 4 weeks. And the remaining 21 were given no Nintendo Wii training and were actually asked to refrain from video games during the same period. And then the 4 weeks, all 42 residents were tested again on the same set of laparoscopic skills. One of the skills, okay, whatever. So here are the improvement, the before, minus, after times in seconds after 4 weeks for the two groups. So we have the treatment group and the control group. The control group are the ones that did not have Nintendo Wii, and the treatment groups are the ones that did have Nintendo Wii. And the question is, does the Nintendo Wii rank training significantly increase the average improvement times? And we are going to use Crunch It to establish this. So we have the treatments and we have the control. So where am I going to go? Which setting am I going to go to? Where am I going to go, do you think? Someone chatted and said stats. Okay, stats. Where in stats? T. Okay, I'm in T. Where in T?
Two sample.
To sample. Okay, what should we call sample 1? Treatment, okay. And therefore control. Are we going to pool our variances? Are we going to pool? Nope.
No.
No, we're not given any information that the sigmas are the same, so we're not going to pool them. We're testing to see if there is a difference, right? Where is it? We're testing to see, does the Nintendo Wii training significantly increase the average? Does the Wii training increase the average? What kind of test are we going to use? One-sided or two-sided? And what would the difference be under the null hypothesis? Anyone? If there was no increase, if it did not help at all, then what would we expect the difference between the two groups to be? Zero. And if there is a difference, if the we training helped, and remember the we training is sample one, our mu1, then what do we expect to occur? Do we expect mu1 to be bigger than mu2, less than mu2, or straight up not equal to mu2? Greater than. If it really helped, then the averages should go up. We expect the average from the first sample, or the population of the first sample, to be bigger than that of the second sample. So let's calculate it, see what we get. First, look at the degrees of freedom that we have there. 34.04, it's a decimal, it's some random number that we arrived at by using that really ooh formula that we hated. But at the end of the day, which of all these numbers is the one that we really care about? We care about the p-value. And what does the p-value tell us?
You mean the definition or what it means in this context?
The p-value?
Yes.
Well, the p-values are just a number. The question is, what can we conclude from the p-value? That's the thing that you want to know in context. The p-value is just 0.003561. The question is, what am I allowed to conclude from the p-value? That's the question. So this p-value, yes, we are going to reject the null hypothesis. My p-value is small. Less than not only 0.05, which is the usual cutoff, but less than 0.01, less than 0.005. I will reject the null hypothesis that there's no difference between the Nintendo Wii and non-Nintendo Wii in favor of the hypothesis that the Nintendo Wii actually does improve skills. Now, if I did a confidence interval for the same situation, 95%. Notice, by the way, I'm still not going to pull them, but I'm going to create my 95% confidence interval. What do you notice about the confidence interval numbers? A lot of the same ones, but there's one thing about the confidence interval numbers that supports the hypothesis test. How does the confidence interval support the same conclusion as my hypothesis test?
Is it because the confidence interval is from 21.21 to 124.9, and then the sample mean for the treatment, or right there it says 132.7?
No, you started off great, but you took a little detour at the end there. You were doing great in the beginning, and then you went off to Nowhereville. But you started off amazing. The confidence interval is from 21.21 to 124.9. And then you said the sample mean is 132.7. But I don't care about the sample mean. I care about the difference of my sample means. That's what I'm looking for. The individual sample means are completely irrelevant. So tell me, what number is not in my confidence interval that actually does matter? There's one number more than any other that is not 73.05 is right smack dab in the center of my confidence interval. No, p-values are relevant. The p-values for hypothesis test, yes, Mary, 0. If the null hypothesis is correct, the difference should be 0. 0 is not in my confidence interval. I am 95% confident that the true difference is from 21.21 to 124.9. I don't know where in that interval it is, but I'm 95% confident it's somewhere in that interval. And you know what's not in that interval? 0. And that's exactly what the null hypothesis claims should be the difference. 73.05 is right smack dab in the middle of my confidence interval. In fact, it's always going to be that way because that's how I make my confidence interval. My estimate plus or minus my margin of error. My estimate here is 73.05. My plus or minus, that's going to give me a range of values that I'm confident might be the true value. And 0 is not in there. So I am 95% confident it's not 0. In fact, even more than that. I feel like if I did a 99% confidence interval, even that doesn't cover it. I did a 99% confidence interval, and even at 99% confidence, it's not in there. It's getting close, but it's not quite there yet. Does that make sense? Yeah, 0 is the null. I want to reject the null. I can only reject the null if I don't get 0. So all you care about is 0 in there or not? And it's not. It's not even at 99%. Make sense? I hope. Okay, so let's stop sharing here. Let's go back to sharing here. So at the end of the day, confidence intervals and hypothesis testing are calculator problems or crunch it problems. We do not do them by hand. We don't want to do them by hand. We don't have to do them by hands. By the way, note, if you do not wish to compute df by this formula, then as a poor substitute, use degrees of freedom equals the smaller of n1 minus 1 and n2 minus 1. Why the smaller? Because remember, a lower number of degrees of freedom will always make your confidence interval wider. Erring on the side of caution is okay. If you're going to err on the side of caution. The actual formula for degrees of freedom gives us an average, a weighted average. If you take the smaller of the two, you're essentially saying this is the worst possible situation. I know it's more than this, but it's not less than this. So I will take that as my number of degrees of freedom. It's the worst case scenario. But the actual formula or the calculator or computer that does it for you automatically is much better. Okay? Questions? Now, from a more conceptual standpoint, what it all comes down to is you have your normal distribution. And if the null hypothesis is correct, remember, we always assume the null hypothesis is correct. So if H naught is true, then what is this number right there? Yes, then that's 0. If the null hypothesis is true, then that number is 0. And when I'm looking, well, for the number that cuts off, for example, right? If this is 5%, if I'm looking for the number that cuts off 5%, then we know what that's going to be. That's like what, 1.645? Well, that would be if it was Z, but this is T. Right? It depends on the number of degrees of freedom. So I'm just going to call this the cutoff point. This is the cutoff point for 5%. It changes depending on what the degrees of freedom is, but that's the cutoff point. And
Yes, sir?
yeah,
Sorry. So the middle, that little middle point, I don't know English today. I don't know what it's called.
and
Where
the
the zero
center,
is. Center. Okay, center. So for when you're comparing two means, is the center always going to be 0?
well, the null hypothesis in all our cases is that mu1 minus mu2 is equal to 0, right?
Yes.
So this is a graph for mu1 minus mu2. If you came across a scenario where where your null hypothesis was that mu1 minus mu2 was something different, then I would go one step further. And well, then in that case, the center would not be 0 anymore. In that case, the center would be whatever value that your null hypothesis is claiming. But in this class, I have never seen a situation where it's anything but 0. But in a more advanced class, it's certainly possible. An example would be, up until now, people who took the SAT and then took my tutorial class and then retook the SAT, scored on average 20 points better. So if you're claiming that you have a better program, or if I made a new and improved version, then the null hypothesis might be that the difference between the new and the old is 20, not 0, it's 20, but that you think it's more than 20. So you can have a scenario where it's not 0, but for all of our examples, it's always going to be 0. Okay?
Got it. Thank you.
Now, your value, this is your value from your data, also called the test statistic, is equal to, in this case, x1 bar minus x2 bar, that is the difference of your means, minus mu1 minus mu2, which in our case is 0, because our null hypothesis claims that this is equal to 0, divided by S1 squared over N1 plus S2 squared over N2. Where does this come from? Well, let's think about it. It's nothing more than the same formula as the z-score formula. Data minus mean divided by standard deviation. It's exactly the same formula. Under the null hypothesis, the mean is mu1 minus mu2, or 0. Your estimate is x1 bar minus x2 bar. And the denominator is the standard deviation of the estimates. It's the standard error. This is no different than before, having z equals x bar minus mu over s over the square root of n. Remember that formula that we had, or sigma over the square root of n if it was z? Or t equals x bar minus mu over s over the square root of n. These were the old, this is the one sample. These are the one sample statistics, test statistics. Where mu, again, is assumed to be 0 as a general rule. All we're doing is extending one sample to 2 samples. It looks a little more complicated because 2 samples is more complicated than 1 sample. It's true. But conceptually, it's exactly the same thing. It's our value minus the mean divided by the standard deviation. The mean is assumed to be 0 if the null hypothesis is correct. And if we know sigma over the square root of n, great. If we don't, we use s over the square root of n, z versus t. but conceptually, it's exactly the same idea as it was before. Let's do another example, just to show you that whatever example we pick, at the end of the day, on your end, the work is exactly the same. So here's another example. Do college students who have volunteered for community service and those who have not differ in how attached they are to their friends? A study obtained data from 57 students who had done service work. So we have service and we have 57. And 17 who had not. No service. And there were 17. One of the response variables measured was attachment to friends as measured by the inventory of parent and peer attachment, which is some score from some standardized exam. These are the results. X bar 105.32 and 96.82 with standard deviations 14.68 and 14.26. Now, the question was, do college students who have volunteered for community service differ than those who have not? Based upon that reading, what is the null and alternative hypotheses for this example? What are the null and alternative hypotheses? We're testing whether or not college students who do community service differ than their friends or differ than other students who have not done community service. What would the null and alternative hypothesis be in this example? Anybody?
Would the null be mu1 equals mu2?
Or mu1 minus mu2 equals 0, but yes. And what would the alternative be?
Mu1 minus mu2 does not equal 0.
Yes. The researcher in this example didn't say that one is better or worse than the other. We get different results. He said, do they differ? I can differ in two ways. I can differ by being bigger. I can differ by being smaller. I don't specify one way or the other. So this is a two-sided test. So how do we go ahead and perform this test? What do we do? What do we do? Just so you know, yeah, two sample t-tests. Go ahead and do it. What's the p-value? 0.04. As a result of that, what is our conclusion? We reject the null hypothesis. In the context of the problem, what will we say specifically? In the context of the problem, what's our conclusion?
That the difference does not equal 0.
Well, you got to be a little more specific. I mean, it's correct, but the evidence supports the fact that the difference is not 0. You can't say the difference is not 0. We don't know that. It's all about what does the evidence claim, or what conclusion can we reach from the evidence. The evidence seems to indicate that the students, whatever the metric was, how attached they are to their friends. It is statistically significant. It's a statistically significant result. Let's go ahead and also do a confidence interval for the same situation. And let's see whether the confidence interval on our calculator, by the way, because we haven't done that yet. Which one on the calculator are we going to use for this?
I'm sorry, what did you say?
We're going to get a confidence interval for the same problem on our calculator. Yep, the 2 sample t intervals, correct. Let's go ahead and get our confidence interval. From where to where is our confidence interval? What do we get? Uh, 95%. If we don't have any reason to claim otherwise, we just do 95%. 0.95. Excellent. 0.358 to 16.642. And as a result of this confidence interval, what do we conclude? What's our conclusion based upon this confidence interval? There is a difference. Why? Why can you say that?
Because 0 doesn't fall in the confidence interval because it's from 0.358 to 16.64.
Excellent. Yes. Reject the null hypothesis again. Here, because P is less than 0.05, and here it's because 0 is not inside of the confidence interval. So in both cases, we get the same conclusion. We just get it in two different ways. Notice, by the way, that the confidence interval is pretty close to 0, which means I was almost going to accept it, or at least not reject it. And the p-value is pretty close to 0.05, right? So both of them were fairly close to the borders. If one was close and one wasn't, I might start questioning things because they're supposed to go hand in hand. So if one is close, the other one should be close. If one is majorly far, so should the other one. Does this make sense?
Wait, sorry, just for clarification. So if 0 was in the confidence interval, we wouldn't reject it, right?
You can't reject it if it's in there because we don't know what number is the correct one. Every number in there is a possible value. So if 0 is in there, maybe it's 0. And therefore I can't reject it because that's what the null hypothesis is claiming it is. Right?
Yeah, thank you.
Yeah, if 0 is not in there, it's like, wait a second, you're claiming it's 0 and I don't catch 0? Sorry, buddy, I think you're wrong. That's basically like, you know, I wouldn't say it that way, but yeah, that's kind of like, yeah, that's kind of it. Looking at the rest of chapter 21, and I don't really see anything more that we need to worry about. Only two things in this chapter are confidence intervals, which we know how to do because we have a calculator, and hypothesis testing, which we know how to do because we have a calculator. So are there any questions on chapter 21? Can you scroll up to the first example? This one here or this one? The other one. The other example. Oh, this one. No, that's one we just did. Which one are you talking about? Which other one? This, I think we only did 2 today. You got it. Okay. Oh, what else can we do today? I guess I can ask some questions here. Let's ask the following questions. Here, I'm going to load up from the textbook again. And we're going to do, let me load this up. So we're going to do, we'll be here. Next one, okay. Okay, let's check our skills. Always nice to have our skills checked. Number 16, the National Assessment of Educational Progress, NAEP, gives a mathematics test to a random sample of 8th graders in the United States. The mean score was 282 out of 500. To give a confidence interval for the mean score of all 8th graders in the United States, you would use A, the 2-sample T interval, B, the matched pairs T interval, or C, the 1-sample T interval. Let's open up the chats. And where did my chat go? Where did my chat go? Here it is. Okay, so in chat, let's see it. I'm gonna give everyone a few more seconds and I'm gonna say go. And then I want you to put down either A, B, or C when I say go. I'll try to do it quick so you don't just see a lot of one answer and do the same one and resort to peer pressure. Is everyone's fingers ready? 3, 2, go. I see a couple A's strewn in, but most C's and lots of abstaining. No abstaining. I want answers from everyone in general. Well, it's too late now because now you just, So the answer is C here. You only have one sample of data. Where are you going to do a second sample from? Right? You have a sample of 8th graders. There's no other sample. It's just one sample. You don't know sigma, so it's got to be T. I wish you weren't given sigma. So it's got to be the one sample T interval. Let's skip 17, which is the same question. Let's go to number 18. My throat's starting to hurt, so you go ahead and read it. And then in a minute, I will say go again, but not quite yet. I need to get a drink. Oy. Oy. Oh. Okay, now I can read it. Okay. So A, B, or C, 3, 2, 1, go. I see a lot of B's. In fact, almost everyone said B. The only person who didn't was Luis Vega, but I can't tell. Were you, Luis, were you for this one or was that C for the last one?
Yeah, I got confused. I was thinking we're doing the other one.
Okay. I feel like I didn't teach this well because everyone said B and the answer is not B. The answer is A. But everyone said B. And I feel like that's gotta be my bad. A matched pair means the same people do both. In this case, you're dividing 40 people into groups of 20 and 20 people do it that way and the other 20 do it that way. But no one person does it both ways. I see a couple O's now, which means I taught it right, you just didn't get it. So I no longer feel bad and now the blame was all on you. So. Yeah, so it's certainly A. Okay, we'll just put this behind us and move forward and we'll just won't tell anyone. We'll keep it to be like a fight club thing. First rule of Math 140 SCI club is we don't talk about Math 140 SCI club. Okay, 21.19. Let's see, one major reason that two sample T procedures are widely used is that they are quite robust. So last class, I talked about robustness. Hopefully you guys remember it. So I'll give you a couple seconds to think about this one. And while you're thinking about it, what's everyone doing for Halloween? Anyone doing anything fun? Sadly, no. Well, that's my life. Watching scary movies, probably. Going to the observatory. Family bonding time. Interesting. I always try to stay away from my family as much as possible. So what do you do for Halloween again? I just listen to Halloween music. I have a favorite singer these days that I kind of have a little man crush on, and I just listen to him pretty much all day long. It's kind of sad. But he does some Halloween. I mean, he doesn't only do Halloween stuff, but he does some Halloween stuff. I just, when I'm driving, it's just, who? You want to know who? All right, tell you what, I'll put his name in chat and I'll put the song. Yes, Mariah, how do you know who it is? You know who I'm talking about?
Was it Boris?
Who the hell's Boris?
I don't know. I thought that's the guy who wrote Monster Bash.
No. This is
When
here.
you get to my door, tell them Boris sent you.
Okay,
Isn't
tell
it
you what.
Boris?
Tell you what, everyone should right now take a couple of seconds. It's a 2.5 minute song. Go on YouTube right now and listen to this guy do the Headless Horseman. And you got to get all the way to the end. And you should also be aware that he does all his own harmonies. So all 4 of the singers in the piece are all him. I'm going to stop sharing for a minute so that I can pause the recording. Okay, recording. So let's finish this problem. So 21.19, A, B, or C, go whenever you're ready. What does robust mean? That's the whole question, right? I mean, the question literally says, this is robust. This means that. I mean, you're basically asking, what is the question asking for? So yes, the answer is B. Robust means that the tests, the procedures still give you good values, even if we don't have perfect normality, which is what we're really hoping for. So yeah, that's just what it is.